Welcome to Lesson 13D, Other Properties of the Blasius Boundary Layer. In this lesson, we'll discuss some additional properties of the Blasius flat plate boundary layer, which are listed here. Then we'll discuss the relationships between local skin friction coefficient, drag coefficient, and momentum thickness. So far, we've discussed delta, delta star, and theta, the three different kinds of thicknesses. Now let's define shape factor H. H is defined as the ratio of delta star over theta. It's a non-dimensional quantity, therefore, since both delta star and theta are lengths. For the Blasius boundary layer, when you plug in our equations for delta star and theta, H is 2.59. This is the case for a zero pressure gradient boundary layer. I note here that H is always greater than 1, since displacement thickness delta star is always greater than theta, the momentum thickness. Well, what good is H? It turns out that H is useful for predicting boundary layer separation. Whereas the Blasius flat plate boundary layer has a zero pressure gradient, we're talking in the general case about flows with non-zero pressure gradients. If shape factor H is small, and by small I mean H close to 1, like 1.3 for example, the boundary layer, if we plot U as a function of Y, will be a very full profile. In other words, a very steep slope at the wall, followed by a more gradual asymptote to capital U. If we look at the slope at the wall, it's very steep, therefore tau W is large. This is typical for boundary layers with a favorable pressure gradient. And by favorable pressure gradient, we mean that it's unlikely to separate. This kind of a profile is resistant to flow separation. Medium values of H, for example, H is around 2.59, which is the value for the Blasius zero pressure gradient case, are typical for nearly zero pressure gradient boundary layers. Finally, for large H, for example, somewhere around 3.5 would be considered large. The boundary profile shape would look something like this, where you have a very small slope near the wall and an inflection point above the wall. Because we have a small slope near the wall, tau W is small. This is typical for boundary layers with an adverse or unfavorable pressure gradient. We call it unfavorable because it's ready to separate. Now let's examine this wall shear stress in more detail. Tau at the wall is defined as mu del U del Y at the wall for this kind of two-dimensional flow. And to find an expression for tau W, we go back to our similarity variables, where we had defined U as capital U F prime of eta, and eta is Y over delta C. What's delta C? Yeah, is delta C the same as delta? It's confusing us.
Well, recall, for arbitrary constant C, we had from lesson 12E that delta C was square root of 2C nu x over U. For C equal 1/2, which is what we used in our Runge-Kutta solution, delta C is simply square root nu x over U. It's not the same as delta, which we called the 99% boundary layer thickness, which is 4.91 square root of nu x over U.
Then delta C has no physical significance?
Well, the magnitude of delta C is arbitrary because we can pick this constant C to be anything we want. And for C equal 1/2, this delta C is much smaller by a factor of 4.91 than the actual boundary layer thickness.
Thank you, sir.
Continuing with our analysis, del eta del Y is 1 over delta C, since delta C is a function only of x. Thus, del U del Y from here is U F double prime of eta del Y, or U F double prime of eta 1 over delta C. Thus, at Y equals 0, tau W is mu U F double prime at eta equals 0, and from here 1 over delta C is square root of U over nu x. This is our expression for tau W, the wall shear stress. But from our Runge-Kutta calculation, F double prime at eta equals 0 is 0.332 to 3 significant digits. This was the boundary condition that we had to guess to get our solution to work out properly. So plugging this into here and letting nu equal mu over rho here, doing a little bit of algebra and substitution yields tau W is 0.332 rho u squared over the square root of Rex. Now let's let Cf be the local skin friction coefficient, which is a non-dimensional form of tau, defined as tau W over 1/2 rho u squared. When we plug in this expression for tau wall, we get Cf is 0.664 over the square root of Rex. This is valid only for the Blasius or zero pressure gradient boundary layer. You may recognize this right-hand side. It turns out that Cf is the same as theta over x. Again, this is true only for the Blasius boundary layer case. This is not true in general, nor is this. I point out that some authors use Cf sub x to indicate that it's a local skin friction coefficient. In other words, it applies at some x location. Now let's consider the drag coefficient, which some people call a global skin friction coefficient. And keep in mind that in all these equations, we're considering only one side of the flat plate. Well, recall from your undergraduate fluid mechanics that drag coefficient is d over 1/2 rho u squared, A, where A is typically a frontal area, but here, since the frontal area is 0, we use instead the planform area, the area looking from the top, so A equal bx, where B is the width of the plate into the page. Since this is a two-dimensional problem, there really is no width, it's infinite, but we can assign some B just to get the dimensions correct. So we need to calculate the drag, again on one side of the plate. We'll do this a couple different ways. We can find d by integrating the shear stress. In other words, d is the integral from 0 to x of tau w dA. Well, we just showed that tau w is 0.332 rho u squared over square root of Rex, and dA from here would be b dx, a small element along the plate. So we can write d equals 0.332 rho u squared, square root of nu over u, b, integral 0 to x, x to the negative 1/2 dx, where we've taken all the constants in this expression outside the integral. Well, this is a simple integral, namely 2x to the 1/2, and when we put in the limits, we get 2 square root of x. And I should have noted that we used Rex as ux over nu to get this. And when you simplify, we get d equals 0.664 rho u squared, square root of nu x over u times b. This is the drag on the plate from 0 to some x location. And thus our equation for drag coefficient, which I rewrite here, becomes by plugging in d and a, which is bx, and noticing that many terms cancel, CD becomes 1.328 square root of nu over ux, or finally CD is approximately 1.33 over the square root of Rex. This is the drag coefficient on one side of the plate, again for the Blasius boundary layer. Let's calculate drag a different way. Recall from some previous lessons when we did the control volume analysis that drag per unit width into the page was rho u squared theta, where theta is the momentum thickness. Well, from the previous lesson, theta is x times 0.664 over the square root of Rex. Thus, d over b is rho u squared times 0.664 times x square root u x over nu. And now we can calculate CD as d over 1/2 rho u squared bx, and substitute this expression for d over b, which I write out here. Again, several terms cancel out, and we end up with 1.328 over the square root of Rex. So again, CD is approximately 1.33 to 3 digits over the square root of Rex. One side comment that we notice that CD is 2 times CF, since the numerator here is twice that of the numerator of CF. Again, all of this holds only for a Blasius boundary layer. As delta grows, the shear stress at the wall continually decreases with x. So the majority of the drag occurs right at the beginning of the plate, and as delta grows, there's less local skin friction since CF is decreasing. And it just turns out that CD is twice CF.
In terms of the velocity profiles, as we've pointed out, the profile shapes are similar, but as we go downstream, they're just kind of stretched vertically as delta grows with x, and that's what causes the slope to decrease as we go downstream. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.